Good afternoon. Thank you for being with us today for this afternoon webinar. My name is Edward Winter, and I'm the Vice President of Remediation Products Incorporated. Today, we're going to have a presentation by Jonas Garcia Rincon on high-resolution site characterization for remedial design and evaluation. Jonas is the site sensing manager at Legion Drilling, which was formerly NUMAC. Jonas received his PhD from the University of Technology in Sydney in a joint program with the Commonwealth Science and Industry Research Organization. Jonas's PhD focused on the use of high-resolution characterization tools in LNAPL contaminated sites. Now, it's kind of interesting, Jonas, there's actually an aside here. I noticed on one of your old journal articles that your first work was done on looking at drinking water quality in Mali. And this kind of coincides with AST, one of the RPI group companies, that the rock truck that sometimes you'll see in our advertisements was put together by an individual named Ray Boyle. And the history of that was fracking rock in Africa to increase the production of water wells. So of course I know that's a tenuous connection. Africa is a big place, but nevertheless, it's really interesting that the things that we talk about and the tools that we use in this industry have a broader application towards good in this world and usefulness in people's lives. Okay, but be that as it may, Jonas, I think it's time for you to get started. So I will hand it over to you. Are you ready?
Yes, thank you very much, Ed, for your introduction, and thank you everyone for joining us today. As Ed said, this webinar will focus on remedial design characterization and especially why adopting high-resolution approaches is important. So there are many topics to touch. I'll try to give a bit an overview, and hopefully we'll have some time at the end for questions so we can clarify or go deeper in any of these topics. And the first thing that I would like to say is, like, many people normally think of direct sensing tools like the MIP, HPT, or LIF when they think of high resolution characterization, but high resolution characterization is more an approach or a framework where we are trying to get results at appropriate scales. But obviously, direct sensing technology is pretty good. Does a pretty good job on that, at least at early stages in the investigation process. So I'll of course go through all these tools and discuss how they work, what are the benefits and their limitations. So first thing that I want to discuss is, like, why should we adopt these high resolution approaches? And the main thing is because any subsurface environment is naturally heterogeneous at multiple scales. Here on the left side, we see a simulation of a fluvial depositional environment and also a photo at a smaller scale of a grain system. And this has important implications for contaminant distribution and of course for remedial design. So one thing that is pretty well known now is how, depending on the permeability of the materials, will have different mass fluxes going through these intervals, and this has implications also for the risk assessment and of course for the remedial design. And this may really change our understanding of subsurface contamination and the distribution of contaminants. So for instance, this is a simulation as well, done in the 90s. The first graph assumes a homogeneous scenario, and I will say it's much more similar to what we normally see in textbooks and university and so on. And it's many times what we have in our heads when we are dealing with a site investigation. But then the figure on the right, it assumes just some heterogeneity in the hydraulic conductivity field, and you can see how that distribution is far more complex than the one on the left side. And I will say that this is more similar to what we really see later in the field when we go and apply any high resolution site characterization tools. This is another example. This one is with field data on a site here in Australia. And you can see 2 logs collected with LIF, with UVOST. That is one of the tools that we will show more in detail later. And the 2 logs were collected less than 3 meters away. But you can see how the impacted interval is pretty different. The intensity of the readings is different as well. And this kind of differences, you can only see them when you are sampling with this very high resolution. If you are just collecting one sample here, you are installing one monitoring well in this area, you don't really know where you are putting it, and you are not going to be even aware of that variability, but it exists. So we have like 2 main objectives, I will say, to simplify it a bit when we are doing a remedial design characterization project. The first one will be, what is the target treatment zone? And for that, using relatively quick tools that can provide very high resolution data is especially beneficial. And this is the main field of application for the direct sensing tools. And then a second question will be how much contaminant mass we have in the subsurface, not just contaminant mass, but also other subsurface properties that we may need to quantify depending on which kind of remediation technology we want to apply. And for this quantification, it may be important to move to other methods, for instance, to conventional soil and groundwater sampling that give us more quantitative information of the subsurface. Obviously, always the recommendation will be to use different or multiple lines of evidence, but yeah, those will be like the main applications of these sets of tools. So first, I would like to say like how we normally face these problems, how most of the industry, I will say in the US, definitely in Australia and other countries, typically face these site investigations, which start with an initial identification of the problem, and then the installation of a limited number of monitoring wells and collection of soil samples. This is normally not enough to gain a good understanding of the subsurface and the site dynamics. And after collecting this first round of samples, we usually start an iterative process where we are trying to fill gaps from previous campaigns when we are expanding our monitoring network and our network of sampling points. But it may take a long time until we get a good understanding of the site. I will say in many cases it's not even really possible doing it in this way, because you cannot really get information at a scale that is significant, that is appropriate for your objectives. So this very often leads to taking this concept from a point of frustration, a moment that usually the site owner may not want to waste more time doing this type of investigation, or there may be another client who bought this land and who want to redevelop that site and may need to get answers and may need to solve that problem as soon as possible. It is when we reach this point that some people then will start considering applying these direct sensing tools or other high resolution approaches, which is probably already too late, well, or very late. You have already spent a lot of resources and time And even after applying this, if you are not doing it in a comprehensive way, and you are not trying to also quantify your contaminant mass and other relevant properties, you are still not ready to remediate your site. What will be a better approach to try to apply these high resolution methodologies early in the project life cycle, and do it in a comprehensive way to also estimate physical parameters, contaminant mass, and optimize the application of any methods that you are applying there. And here we are like decreasing project life cycle that could take years to something that it may be done in months, depending a bit on the site, of course, and avoid this frustration and this problem with clients. Also showing an interest in solving these problems as well as we can, and differentiating us from other competitors that may be working in the same field with conventional approaches. So now I want to go a bit more in detail in all this direct sensing technology and why it's so relevant for high resolution characterization, and also discuss some of the limitations that it has. So we are mainly talking about probes with some sensors that can be used for the measurement of certain hydrogeological and contaminant properties. And we push these probes using usually direct push technology into the ground. So this will be a bit the first and one of the most important limitations. They are designed, since we are applying direct push technology, they are designed for environments where we can use this methodology that is usually mainly unconsolidated materials or extremely weathered rocks. Sometimes it may be possible to use them, but obviously in those cases you are already decreasing your productivity, so they are not designed for that. And they are also designed for relatively shallow investigations, so usually the limit is in 20-30 meters, although sometimes they can go a bit deeper. So we will push these tools into the ground. I took this slide from Dakota Technologies, and while you are pushing the tools into the ground, you are measuring these properties and you're getting a log in real time that you can access. Usually the setup will be, we will have this geoprobe rig, and then usually a support vehicle where we have all the equipment to process and see the data. The probes have a cable or set of cables and tubing going through all the rods, different connections depending on the type of tool that we are considering, and all these cables are going into the support vehicle where we have the different direct sensing equipment. What are some of the main benefits of these approaches? First one, obviously, the high density of measurements. We are collecting measurements every 1 or 2 centimeters. Then the rapid data production. We push the tools at 2 centimeters per second, mainly. And this means that we don't only have very high resolution results in the vertical profile, but also that we are able to cover a wider area in our site. We are able to investigate more locations. So it helps to increase a bit the horizontal resolution as well. Then I like to talk about precise delineation, because these tools are mainly qualitative or semi-quantitative, but they are pretty good as well to delineate some subsurface features, and sometimes better than other methods that are considered quantitative, because it doesn't matter if we are talking about coring that will have some errors and uncertainties related to, for instance, poor core recovery or loss of fluids, or cross-contamination, and so on. Or if we are talking about the installation of monitoring wells, that the screen needs to be installed in the target intervals that we want to characterize. If we are getting information at a scale that is not adequate. So in this case, for instance, if we have some monitoring wells installed and it's a site with El Napel, if that El Napel is not mobile or it's present at a sub-atmospheric pressure, it will then access our monitoring well, and we will see some high concentrations in the well likely, but we will then see an Napel, and it's there. And in that case, if we are using a different tool like LIF, for instance, we will find it. So this is an example of how all the tools have certain limitations. Obviously, some are more quantitative than others, but ideally, I will say the recommendation will be to use multiple lines of evidence and try to interpret all of them. Another important benefit of these tools, as I say, is that we are able to visualize the data in real time. And this means, well, here, for instance, I have a video, but the normal speed is actually even a bit low. We are going like only 1 centimeter per second here with LIF. And you can see how you start obtaining here some higher readings that reflecting the presence of Napel in the subsurface. This is a very different approach to going to the site, collecting our samples, sending them to the lab, analyzing them, and then a few weeks later realizing that you didn't put your sampling locations where you had to put them, or that you are having results that you didn't expect. Then you need to go back to the site and fill these gaps and so on. So this means that with these tools, we can do adaptive field plans. We can choose which tool we are going to use in the next location, or where we are going to put the next location. And this is obviously very beneficial to make the most of our time on site. This also means less gaps, less uncertainties. And another important thing also related to the concept that I mentioned before of applying these tools early in the project life cycle is that these tools, since they are pushed with direct push technology, produce minimal waste. So they are really great tools as screening methods, and they don't produce this waste. So if we are investigating sites and we are trying, first of all, to find out if that site is contaminated or not, in many cases it doesn't really make much sense to go with some conventional approaches that may have more negative impacts than what is really in the subsurface in that site. And then, of course, one of the main advantages is the optimization of other methods of remediation design and application of all the physical sampling methods that are usually a bit slower and they produce more waste and so on. So you can apply these direct sensing tools first, and with that information, then you can go with the other methods and do everything in a more optimized way. This, for instance, is a research project in Europe a few years ago from ENISA, that is a direct sensing contractor there, and they compare the costs of a conventional investigation and an investigation using MIP and their direct sensing tools over the same time in the same site. And I like this because obviously if you do a good characterization, you are going to be able to really optimize your remediation system, and you may be able to have great savings, and this changes from site to site. But what I like from this one is that it's comparing just in the investigation phase and actually over just one campaign, how you are saving money in other aspects like the installation of groundwater wells or sampling. I don't know if they include the waste associated costs here that can be pretty significant, at least here in Australia. And they are showing how you can even get lower cost using the high resolution approach which is still accompanied by some physical sampling in this case, which will be much more relevant during a remedial design characterization phase. And of course, collecting all this high density data means that we can build 3D, 4D visualizations far better than using limited data or data collected at slow resolution. This will be the same if we are just collecting physical samples, but we are using a high density approach. And this is very good for stakeholder communication, especially with stakeholders who may not be experts in this field, but having this kind of tools will really help to communicate your outcomes and what you want to do in the project. And I'm going through a few of the most relevant tools very quickly. The first one will be the hydraulic profiling tool, or HPT. That is this kind of probe with an injection port. They often have an electrical conductivity sensor, and we are injecting water in the subsurface while we advance the probe into the ground, and we are measuring that injection flow and the pressure that we are inducing. So this kind of information, in this case, we will get like this log. The green one is the pressure, the blue one is the flow, the black one will be the electrical conductivity. This gives us information about the permeability of the materials. If we have low flow and high pressure, those are low permeability materials. And if we have low pressure and steady flow, that would be more permeable materials. Electrical conductivity typically gives information about the presence of certain clays, but can be also influenced by other factors. But it's still good to have it as at least a secondary line of evidence or an additional line of evidence. With this kind of information, we may use some models to estimate hydraulic conductivity. Again, I will consider this semi-quantitative method. We can also, once that we collect multiple logs, we could build cross sections or 3D models. This is an example from a El Napel contaminated site where we applied some mass recovery methods. And in this case, for instance, near this log, HPT 64, that it shows like less permeable materials across large intervals of the profile. Near this log, we will typically observe confined El Napel conditions, very low permeability, very low Napel transmissivity and recoverability, while in other locations, like near HPT 73, we never saw confined El Napel conditions, and the El Napel transmissivity was the highest in the site. I'll give a bit more of detail on this later. Obviously, it may be difficult just from this data to reach that kind of conclusions. Because of that, it's good to also complement this with other methods. But it's true that you get information that is very consistent with your potential remediation performance, and you can get that in just 1 week of works, a few days. This slide is mainly about the dissipation testing, because the pressure that we are measuring is not just the pressure that we are inducing, but it's also influenced by the hydrostatic pressure and the atmospheric pressure. But I don't want to go too much in detail with this one. And here what we see is a model to estimate hydraulic conductivity, the one that is normally used and that is implemented in the GeoProbe software. So this was mainly a calibration between the slag tests conducted at a few sites in the United States and HPT profiles completed in adjacent locations. And you can see that there is obviously some error and some uncertainties. And of course, the model was built considering the data from these specific sites. So in other sites, it may be interesting to build your own site-specific calibration instead of relying on these ones. There are also some equations that have been recently developed also for the estimation of hydraulic conductivity. But as I say, in all the cases, there are some uncertainties involved, like in any other methods to estimate hydraulic conductivity, and one should be aware of that when interpreting the results and designing the management strategy that is going to be followed afterwards. Obviously, very important from this HPT tool is that it's giving you information about preferential pathways and low permeability zones. So then you can use a sampling method like discrete groundwater sampler like the SP16 to collect samples from these points, or other tools like the HPTWGS or the Waterloo APS to collect samples and get information at specific intervals instead of use long screen wells. Another tool, a bit more recent in the environmental industry, will be a nuclear magnetic resonance, where one is applying a magnetic field in the frequency to induce this precession movement of hydrogen atoms. And in this way, we can measure like an intensity and a decay over time. And this gives us information on the presence of water. We are able to measure. This will be the kind of log that we could get, and we are able to measure water content with it, and also depending on the decay, what type of water we have, if it's like absorbing clay, if it's capillary water or mobile. Having that information can be used for some models to estimate hydraulic conductivity as well. It does it in a wider range than HPT, especially like the upper limit is much higher than with HPT. And here you can see a bit of comparison, hydraulic conductivity values, nuclear magnetic resonance and HPT. At the same time, seems to be a bit slower method than HPT. You don't need to inject water, which may be good for some sites. And interesting for the topic, today's topic of remedial design characterization, it has the potential to quantify NAPL saturation in the subsurface. This is because the nuclear magnetic resonance readings, that are mainly these spin relaxation values, are influenced by the diffusion and the diffusivity of the fluids that are in the subsurface. So here there are some experiments that have been conducted by Vista Clara in the US, where they had like only water in this first case, and then they mix water with oil, and you can see how the readings show some differences. So this can be used to estimate also LNAPL in the field, at least potentially. Is something still in development. Another tool will be the membrane interface probe, or MIP. This tool has a heating block, so it hits the ground to 120 degrees in general, and this induces volatilization of any bugs that are present in the formation, which will move through a semi-permeable membrane, and they will be carried usually with nitrogen up to the surface, where we have a gas chromatograph with different chemical detectors. A pretty common setup is with the PID, FID, and XSD. That will be a halogen-specific detector for chlorinated, brominated compounds. And the values, as with the other tools, are semi-quantitative or qualitative. Obviously, in some cases, there may be relatively good correlations in some locations with physical samples, but this is something that probably you need to get to have quite homogeneous conditions in your site, and sometimes, or I would say most of the cases, it's really difficult to really get quantitative estimation of your contaminant concentration from this type of tools, because there are other factors influencing the readings. But it's true that since you have these different detectors that can give you an idea of the type of chemicals that you have, for instance, TCE will respond in the XSD and the PID. If you have chlorinated alkanes, you will only see a response in the XSD, but not the PID. And then also important for the evaluation of remediation and natural attenuation effects. You have fields with aromatic hydrocarbons. You normally have a high PID-FID ratio, and when they are weathered, that PID-FID ratio tends to decrease. So that's important aspect that can be checked if you are applying or if you are assessing the natural attenuation of a site. And also, like, you can delineate the presence of methane, also important in sites with petroleum hydrocarbons that will only respond in the FID. This is a table with some of the compounds and some of their main properties affecting MIP results. And here we see a log, an MIP log, where this column in blue corresponds to the PID, and the next one to the FID, the last one on the right side to the XSD. So we can say that this is a site contaminated with petroleum hydrocarbons because of the absence of readings in the XSD. And it's also a quite typical profile where we can see an increase of electrical conductivity, probably lower permeability materials being present at the top of the profile, and then the petroleum hydrocarbons, possibly there could have been some LNAPL on site being present just below these lower permeability materials that may be confining or constraining the vertical migration of the contaminants. And the last tool that I want to mention, the LIF, laser-induced fluorescence. Well, there will be a few different probes using this type of technology. Here I'm going to focus mainly on the UVOST one, but you also have like Targos for heavier products, or even DILIF for non-fluorescent compounds. But they all have relatively similar design and some fundamentals that are shared between all the tools. So in the case of this UVOST, we'll be generating a laser that is delivered to the formation using fiber optics, and this will excite any compounds that have the ability to fluoresce. And this is, for instance, the case of PAHs. So we will excite them, and then we will measure how they emit the energy that they absorb when they go back to their equilibrium state. So we will have like an intensity again and a decay of that fluorescence that we are able to measure on site. In the case of UVOST, what it does is to collect this information at 4 specific wavelengths, and each wavelength is characteristic of some specific PAHs. Usually the shorter wavelengths, 350 nanometers here, it's giving you information about the lighter PAHs, like naphthalene, for instance, while the longer wavelengths give you information about much heavier PAHs. So taking a look at these waveforms, you gain some information, not just of the presence or absence of LNAPL, but also the type of LNAPL and even the weathering degree, especially in the case of gasoline. And this is also influenced, since you can get some information on the weathering degree, you also see effects that may be attributed like to natural south zone depletion and natural attenuation mechanisms. So it's not uncommon. For instance, in this profile, all this area will correspond just to natural soil fluorescence that one could decide that that's natural soil fluorescence, mainly because the lifetime is very short. That's very typical of like calcareous sands, for instance. But then we have here, for instance, this narrow interval that it has a bit longer lifetime. It's also slightly blue shifted compared to this, shifted to this 350 nanometers channel. So this is NAPOL. But if you see in this case, the blue channel is very small compared to the other ones, and this is because this is in the bad ozone, and this NAPOL mask has been quite degraded compared to the NAPOL that you can find then around the water table and below, where you can see results that are much more blue shifted, where this 315 nanometer channel is more significant than the other ones, and that is the predominant one. So this gives you, as I say, some information not just on the NAPOL distribution, but also on other subsurface characteristics. This can be plotted like in these plot maps, that it will have lifetime in one axis and the waveform or the color of the fluorescence in the other axis. And you can see how this is a bench scale experiment where, since the contaminant, this gasoline, is being degraded, you can see how there is a shift towards the longer wavelength values. So you have like this red shifting here. And a final slide for these direct sensing tools will be this one showing the application of UVOST again in sites where BOST 200, it's one of the RPI products, have been applied. Well, this is bench scale testing as well. And you can see how the presence of BOST 200 influenced the UVOST readings. So for instance, here we have clean sand, and we have like very low like background fluorescence. But when we put BOST 200 in this clean sand, this was done by Dakota Technologies, the signal practically disappears. So it could be a way maybe of assessing where BOST 200 has been in place in a quick way. And then we have here 3 sets of data with 3%, 30%, and 90% of gasoline that was mixed in soil samples. These ones at the bottom will correspond like to the pure gasoline with any BOST 200 applied to them. Then the ones above correspond to a small amount of BOST 200 being applied to these samples. So you can see 2 things. First, how the signal decreases. So for instance, 3% practically disappears, 30% it really decreases quite a lot, 90% decreases a bit as well. And you can also see how the signal, the type of fluorescence change, how the signal blue shifted because of how the BOST 200 is sorbing some of the compounds. And here at the top, you have a bit the same type of experiment, but just with a greater amount of BOST 200. And you can see how the fluorescence decrease even more. So in this case, the 30% gasoline sample has a fluorescence that is really, really low. So as we saw during this presentation, these direct sensing technologies provide some useful information that can be used during remedial design and also for the evaluation of remedies or natural attenuation, but they don't substitute physical sampling. As we saw, most of these methods are to a great extent qualitative or semi-quantitative. There are other approaches that could be used to quantify or to improve the estimation of contaminant masses, similar to what we saw. For instance, the use of nuclear magnetic resonance or the use of portable GC equipment and mass spectrometers like the one in the case of the GC that we use for MIT. RPI, what they do for their projects using BOST 200 and other RPI products is that they provide analytical services as part of the remediation project. So one can follow this high resolution approach, but collecting hundreds of samples that can be sent to the RPI laboratory and be analyzed, and then you are able to quantify your mass, and then you are able to really design how you are gonna apply your remediation method. In these cases, direct sensing logs could still be used as auxiliary data, but it shouldn't be like the only data set to design, for instance, the injection of activated carbon as a remedial amendment. But yeah, it's always good to have like multiple lines of evidence that help you to interpret your site and get a bigger picture of what's going on in the subsurface. And here, just to finish, two very short case studies, in less than 5 minutes. This first one, I don't want to give much detail. We published some papers about the investigations and the remediation in these sites, but I wanted to show this figure where we collected some logs with UVOST and soil samples in adjacent locations, and we really didn't find good correlation. This will be the response from UVOST, and this will be the NAPL saturation as estimated from coring. As you can see, there is no clear correlation. It's true that if you go like to the specific areas where the UVOST and the cores were collected, here they are called A, B, and C. You can see, for instance, that the measurements are mainly here. The measurements for the area B are around here, and the measurements for area C are around here. And there are obviously errors involved in the application of both methods, but I think it shows that even if in some locations you could get reasonable to some extent correlation, that doesn't mean that you are going to be able to estimate contaminant volumes across your entire site just by doing direct sensing. What we found in this research was like the UVOS responses are influenced by other parameters, and usually you get higher responses in coarser texture materials. We found like bigger UVOS peaks in areas with high transmissivity and relatively low responses in areas with low NAPL transmissivity, because these low NAPL transmissivity areas were associated to more like finer texture materials, while the higher transmissivity areas, of course, were associated to coarser texture materials that also influence the UVOS response. And another, the last case study I want to show, it will be here in Australia as well, in Queensland Petrol Station. Presumably really a homogeneous site, like clean sands. They have been doing a few years of conventional investigation before we went to this site. They had well screens installed down to 6.5 meters below ground level, and there were no indications of NAPL at that moment. And there were plans of using in situ chemical oxidation in those top 6.5 meters of the profile. We went there and we applied UVOST and MHPT. That would be the combination between MIP and HPT. What I like about this case is that these are the first locations that we did in the first morning, the first UVOST log, the first HPT log. And just with this data, so it's not just to have this high resolution, many locations, but also the different type of data that you are collecting. Just with this, we could get quite significant outcomes. So for instance, we found that NAPL was mainly below the water table, that was around 6 meters in this site. And we can see here how it goes below this 6.5 meters. That was exactly where the well screens were installed. We could see as well how this was associated to a preferential pathway here in the HPT pressure. You can see how the pressure decreases just at that interval. This doesn't mean that the preferential pathways are the intervals with the lower HPT pressure in your profile. Obviously, there is a history behind that release, but what you usually find is that there are areas of lower HPT pressure, higher permeability, if you want, compared to the adjacent sections of that profile, and that's where the contaminants preferentially go. And this presence of NAPAL was also supported by a very high PID responses. We could identify NAPAL as gasoline, even if the responses were very low, but you could, as I showed before, check these waveforms to interpret what type of product you have, regardless of the intensity. We found an NAPAL, it wasn't like an isolated location that the walls didn't pick up. We found it consistently across a 25-meter transect where few walls were installed, and we could recommend to target the injection. In this case, because they wanted to use ISCO alpha, that obviously have some limitations in the presence of NAPAL, but we could suggest target injection below that area where they wanted to do it, and focus on the areas that were more contaminated and where the preferential pathways were found. Because obviously, if here you inject any chemicals or any other amendments at low pressure above 6.5 meters, everything will stay there because you have this lower permeability layer constraining the movement of those amendments to the areas that were really contaminated. And that's it. I try to touch a lot of topics. If you want more information of direct sensing technology, the ITRC released a really good guide in 2019. It's a pretty good reference. In our website, we have a few free webinars as well, and we'll soon release a book mainly on the investigation and remediation of petroleum hydrocarbons that will go quite in detail as well in aspects related to high resolution characterization. So that's all from my side. If you have any questions, I will be happy to try to answer them. Thank you.
Jonas, I appreciate it. If any of you guys have questions, we'll just stay on. I know some of you may have to go on to other things. Nevertheless, just type your questions in the question box and we'll get to them. And in the interim, so Jonas, there are multiple messages here, but we'll start with one of the first ones, and that is that you could save your client a ton of money if you use these tools early as guides to installation of monitoring wells and ultimately guides to the collection of soil or aquifer sediments. So we talked about that, and it's important. Now I'm going to throw in the commercial part, of course, that I need to, but RPI Laboratory is more than willing to process your soil and aquifer samples and your water samples, even if you haven't committed to use a BOSS product. So that is available to you. You contact me if you're interested. But going back, you pointed out that in Europe they showed that there was this particular savings, and I can't really remember immediately which document it was, but it was one of the U.S. military documents, and they showed the same thing. They showed that if you use these tools early in the process, instead of kind of futzing around and doing this random monitoring well placement and random soil sampling, if you will use the tools such as MIP, UVOST, HPT to figure out early on the characteristic of your site before you do all that other stuff, that you can save 25%. At least that was their estimate. So, I think that was a very important point. The other important point that you touched on in multiple places was that the transmissivity of the site, or the characteristic of the stratigraphy, greatly influences the way you need to look at the information you might draw from each of these tools. And I'm going to kind of throw that out as a chance to let you talk a little bit more while we see what questions we have come in.
Yeah, that's right. As I say, I mean, these direct sensing tools are really great to find impacted and unimpacted areas, to really quickly investigate the distribution of your contaminants on site and everything without producing any waste. But the results are influenced by different parameters, multiple parameters. So that's important to keep it in mind when you interpret the results. I see that there is another question a bit in this line as well, like about how often the confirmatory samples are not well correlated with the direct sensing readings, and this really depends on your site, the heterogeneity of the site. So if we talk about UVOST, for instance, some of the parameters influencing the reading is the type of contaminant, not just of which waveform you get, depending on the hydrocarbon mixture, but also the intensity. Diesel usually shows much higher responses than gasoline, even if you could have the same mass or the same saturation in your site. Other parameters that affect are the type of soil. If you have clays, that doesn't enable the laser to travel that far away. The clay also may partly hide this and you will have more complex distributions in finer grain systems. So that's obviously something that can also affect. And there are a few other aspects. In terms of transmissivity, this is totally linked to what I mentioned now about the permeability. I believe it also influences in some way the MIP results, mainly because of my personal interpretation when I see some of the logs and areas that show like values that seem too high compared to what it's expected or what other lines of evidence suggest. But I haven't done like any control experiments or research on that, so I wouldn't like to confirm anything in that regard. But definitely, I mean, if you think of how, for instance, the MIP works, it has this heating block, heating deformation. So depending on the type of materials, this heating process will be different, depending on the type of contaminants as well, how you have those sorption and desorption mechanisms going through the membrane of the tool that could be affected as well. The main point is how relevant these factors are, because some of them may not be really influential for how the tools operate. For instance, like regardless of if you are in the BADU zone or the saturated zone, both the MIP and the LIF technologies typically give results that seem pretty reasonable, although there are obviously different physical processes happening there. And this also can affect sometimes physical sampling or collecting cores, depending on the type of material that you have. You have less or more core recovery and so on. So yeah, I think it's an interesting field to do further research, but at the same time, the results that they provide are really great and valuable compared to using conventional low resolution approach.
Okay, so now we got quite a few questions, so we'll have to be a little shorter with our answers. But nevertheless, this question is similar to what you've just said, but it's more specific. And that is, how often is it that your MIP data does not correlate with your hard samples? So if you if you were to try to correlate MIP to soil samples sent to a lab, and then you get two different answers, you know, try to describe how often you see that, and what do you tell your clients?
Yeah, that's right. I think that one of the most interesting parts in the question is actually what you tell to your clients, right?
I think so. Yeah.
They get a bit surprised when they get this variability in the results between different tools. But I mean, I don't like to use very often the term confirmatory sample because they are different methods measuring different things in different ways, presenting them in different units. Most of the cases in most of the sites that we investigate, when we try to do this investigation and this comparison, actually the physical samples, the groundwater soil samples, have been collected using a low resolution approach, using maybe long screen wells, or in areas that are not the same. So it's something that actually you cannot compare straight away. Ideally, if you want to really compare these different methods, you can, and Dakota Technologies, for instance, has very good information on that, like to extract the cores, and you can apply your tools directly in the same cores. You could see, for instance, you check the fluorescence of those cores in the surface, or you could collect samples and use UVOST to get a response specifically for those samples. And then is when you are really correlating, like apples with apples, and not different types of data from different areas. Because sometimes the heterogeneity, and this goes a little bit with the start of the question, how often the samples don't not correlate with the MHPD or any other direct sensing results. That totally depends on the heterogeneity of your site and the variability in your site, and it's often, I find, very complicated to say in advance what type of site you have. Obviously, you could have an idea depending on the depositional environment and so on, but until you are not there and you are not collecting the data, I find it really, really challenging. And yeah, in some sites, you are surprised because you are just collecting a few logs every 10, 15 meters, and they correlate relatively well. And then in others, you are collecting logs every half a meter, maybe, because you are interested in a specific area, and every log is showing some strong differences. So as I say, it's totally site-specific.
Yep. So here's an interesting question. The picture that we put out to announce the presentation, it was your opening paragraph on your slide stack here. We've been asked to explain that picture if we could. Other than it's very cool looking, right? That's why I put it on the presentation.
Give me 1 sec. This again. This one, right? This one is actually from Elskov, Danish company. So it's from a software that they develop in-house, and that it's currently used by them and also AST in the US, I believe.
Yes,
so this is mainly a system. It's obviously like a 3D visualization tool, like many others that you can use to interpolate your data and estimate volumes and so on. But it's also specifically designed for high resolution projects and injection remediation projects. So you can, and these circles give an idea like of how much amendment you want to inject in each location and how much you are actually injecting. So it goes with a database. You can go with a tablet to the site and monitor what you are doing. So you have all the information there of what your plan is, and then you can update that with the type of information that you are getting on site. So this specific figure here is showing these ISO contours will correspond to the contamination and the target treatment zone, and then these stacks will be injection points distributed across the target treatment zone.
Okay, so I'm going to kind of combine a couple questions here. One of them is, can you describe the difference between OIP, that is a different tool which uses a LED, a high intensity LED light, versus UVOST, and might as well combine with that, how many solid soil samples or what technology would you be using to, well, I hate to say confirm, that's not really the word, but to ensure that you're getting an accurate picture of your site?
Yeah, so regarding the first question of the OIP, because mainly compared to LIF technology, the main difference is that LIF is transmitting, delivering this laser to the formation, while OIP has a ultraviolet source, but it's not a laser. From that point of view, what you get in OIP will be like the intensity of the fluorescence, but you don't get these waveforms at different wavelengths and decay or lifetime values that give you information about the type of hydrocarbon or other subsurface properties, presence of oxygen, and so on. So OIP mainly give you this intensity, total intensity value. I believe the GeoProbe is working towards developing the tool further and be able to analyze the data in more advanced ways. But yeah, at this stage, I will say that the main difference that you are seeing the intensity. And if you remember one of the slides I show with UVOST data, and I start talking about natural soil fluorescence, for instance, that's something that is very easily seen when you have the waveform, because I didn't go in detail into that in the presentation, but depending on the type of waveform, there are some that are characteristic of soil materials, and others that are characteristic of diesel, and that is characteristic of gasoline. So getting that information with OIP is at this stage a bit more challenging, I guess. I may be wrong because I don't really use OIP myself here. And then also it has a camera recording the data visible camera, so it's missing some information in the ultraviolet range of the spectrum, which is especially important for light products. But at the same time, it's giving you these snapshots of the subsurface, so you could stop the camera at any point and get a snapshot where it can give you some additional information of the soil materials. It's something that people normally like to see, to have a picture, be able to see the sample instead of this abstract data that we normally collect. But yeah, I would say those are the main differences. And then regarding the other question that was about the number of samples, right? To do the remedial design characterization.
Yeah, probably.
Again, I would say that.
Go ahead.
Yep. No, what I would mainly say is that it depends a bit on your site, because as I said, there are sites that present a higher variability than others. I think from that perspective, using direct sensing tools at first may give you a good idea of what type of site you are dealing with, and then how good your resolution should be for this. But then you could enter it also like in a tier approach or something like that. So it depends a bit on the project characteristics. Usually it's good to get samples every few meters.
Kind of, yeah, sorry to interrupt you, Jonas. Yeah, it's a very difficult question to answer really, but so let's get a couple more and then we'll call it done. One of them, this is probably a pretty good question here. Not that the others weren't, don't misunderstand, but how does the penetration of the LIF into the sidewall compare to the influence of the MIPS heater block? Now, I think
the penetration of the tools.
Yeah, compared to the.
Well, I mean, both tools are.
No. Let me reword it for you. Here's what I think that Dan can intervene here if he wants, but here's what I think he was actually asking. You know, when you have an LIF, it has a limited window, and then you look at a MIP. A MIP has a large heating block, and I think he's asking, even though the MIP actually has a small port, despite the size of the large heating block, I think he's asking, you know, how does the LIF's ability to look at a base of support of versus a MIP's ability to look at a similar thing. I believe that's really what the question is. I do your best with it.
It's a really interesting question. Unfortunately, we don't have much data to really support that. I mean, that should be probably tested like laboratory scale or something like that, because in the field you cannot really control many of the variables. Right. I agree that the LIF, since it only has this small sapphire window, that may that give you really high resolution if you want data from that point. So the support scale, the measurement scale is quite small. In the case of MIP as well, maybe a bit bigger. In the case of MIP, one interesting question would be also like how, in the case of UVOST as well, how pushing the tool into the ground in different types of soil, because you can have like contractive or dilative materials that are terms that are more commonly used in geotechnical engineering and not so much in the contaminated land industry. But I believe that could help, that could have an effect on the type of readings that we get. But as I say, there is not much research backing up that or giving more insight into that. There is a difference here that may be relevant with when comparing these tools, for instance, to monitoring wells, that obviously, especially longer screen wells, have a much larger sampling scale, support scale, if you will.
Right.
And sometimes you can get NAPAL in a well because that well has been installed there over the years, and there might have been some NAPAL at some time that have been mobile enough to go into the well, and then you go with UVOST and it's difficult to find where it is. One reason for that is that with this direct sensing technology, you are getting a very precise snapshot of the subsurface at the moment of the investigation. Well, these wells give you a more average, if you want to call it like that, response.
Well, so we'll tie this up with Marcus's question as your last question. I'll help you out with this a little bit if you need it. But what he asked is a pretty good question. You know, we want to use multiple lines of evidence for what we're doing. You have multiple tools that you're using, but yet the information you get from the tool, very similar to, say, if you used MIP and LIF, the information doesn't correspond directly, right? Sometimes the information even seems to contradict one another, but yet you have to build this into a picture to present it to your regulatory agency. And I think Marcus is saying, man, do you have some pointers in how we help guide the lesson form, understand why these various forms of information are always telling you exactly the same story? In his particular case, as far as the question goes, he was talking about explaining the fluorescence to the less informed audience.
Yes, it's obviously important in some projects. We haven't had many issues here in Australia. but yeah, I guess it's also like a long process to increase the awareness about these methods and how they work and what type of information we get. And they are not new, they have been with us for several decades now, but there's still not as much awareness as there should be in the industry and in the regulatory space. So the main problem is thinking that you are gonna obtain exactly the same information regardless of the method. And if it was like that, there would be no reason at all to adopt a multiple lines of evidence approach. The main thing of the multiple lines of evidence is to acknowledge that all the methods have some uncertainties and some errors, and use that to be able to make more informed decisions and to be able maybe to design worst case and best case scenarios, gaining a bit of insight into that. So I think one of the problems has been probably to oversell some of the applications of these tools, because obviously if you say, oh, these results that we are going to obtain with this particular tool are going to be 100% accurate and is giving you the true image of what's going on in the subsurface, and then you start applying another one that they are saying the same about the other method and you have some inconsistencies, it's really difficult to tackle with that problem. But yeah, I think it's a matter of time. I think obviously the popularity of many of these direct sensing tools have increased over the years, and it will be a matter of time that we use them more regularly, and that the regulators also want to see them apply more regularly. I would say many of the regulators, what they don't want to see is poor sampling strategy or anything like that. So
yeah, I would
there
say
are some that are more that they are not very keen to use this tool, but there are others that are exactly the opposite. So yeah, it will be a matter of time.
I would say this, that more and more regulatory agencies are coming to understand the value of the tools. And the earlier you use these tools in the process, the easier it is to understand. Okay, so if early in the process you use, and I'm just making this up, you use UVOST, MIP, and HPT, and let's say you use resistivity to show where your bedrock or confining layer is, and you put that picture out, and then you say, now what we need to do with this picture is go and collect our hard samples. Now what we need to do with this picture is put in our monitoring wells, an informed placement of the monitoring wells. You then start to separate the houses in which the two sets of data live. And it's easier for the regulatory community, it's easier for anybody to understand at that point what you're doing. When you're trying to present a mix mash of the two datas, sometimes people get confused of wondering, well, why do I have them both? But all of that's just a matter of education and time, and there's a perfectly proper place for each of these tools. Jonas, I sure appreciate it, and I'd like to say to you 59 persisters who have lasted till the very end of this thing, I sure appreciate your time. I hope our going over didn't indicate otherwise. Jonas, thanks a lot, man.
Thank you very much. Thank you, everybody.
And have a good day. Yep.